When most people hear the term acids and bases, they usually think about something like stomach acid or soap. However, there's actually more to it than that. According to the Bronsted-Lowry definition, an acid is a substance that donates a proton in the form of hydrogen ions, while a base is the substance that receives the hydrogen ions. These attributes of the acid and bases are what makes them react to each other and results in conjugate acids and bases. The term conjugate pair refers to two substances that differ only by the presence of an extra hydrogen ion. An acid forms a conjugate base and a base forms a conjugate acid. Take, for example, the reaction between hydrofluoric acid and water. In this reaction, the hydrofluoric acid acts as an acid and water acts as a base. This may sound counterintuitive, but water can act as both an acid and a base due to its unique ability to both receive and donate a proton in a given acid-base reaction. Regardless, the reaction results in a fluoride ion as the conjugate base, while the hydronium ion can be identified as the conjugate acid. While the Bronsted-Lowry definition is widely used in the field of chemistry, it has some limitations, namely the fact that it can really only be used to define acid-base reactions involving hydrogen ions. This is where the Lewis definition of acids and bases comes in. In the Lewis definition, an acid accepts a pair of electrons, whereas a base donates a pair of electrons. This broader definition can provide a wider look at acids and bases involving substances that do not exchange hydrogen ions. Interestingly, all Bronsted-Lowry reactions are also considered to be Lewis reactions. However, the reverse cannot be said. An example of a Lewis acid-base reaction would be the reaction between a fluoride ion and boron trifluoride. In this reaction, the fluoride ion acts as a Lewis base while the boron trifluoride acts as the Lewis acid, creating boron tetrafluoride as the acid-base adduct. Lewis acids are electrophiles and have electron-poor pi systems, while Lewis bases are nucleophiles with electron-rich pi systems. One final thing to note about acid-base reactions is that charge is always conserved. When two substances react in an acid-base reaction, the formal charge of the acid decreases by 1 because it lost a hydrogen ion or gained a pair of electrons, whereas the formal charge of the base increases by 1 because it gained a hydrogen ion or lost a pair of electrons. Regardless, the sum of the formal charges of the reactant should be equal to the sum of the formal charges of the products. For example, in the reaction between hydrogen fluoride and water, both substances begin neutrally charged. However, the products contain a negatively charged fluoride ion and a positively charged hydronium ion, resulting in an overall neutral charge. Similarly, in the case of the reaction between a fluoride ion and boron trifluoride, the negatively charged fluoride ion reacts with the neutrally charged boron trifluoride to create a negatively charged boron tetrafluoride ion, maintaining the conservation of charge in the reaction.